Welcome to the lesson on circles. At the end of the lesson, we will be able to define circle, understand the terms related to circle, prove that equal chords of a circle subtend equal angles at the center, prove that the perpendicular from the center of a circle to a chord bisects the chord, prove that equal chords of a circle are equidistant from the center. Prove that there is only one circle passing through three given non-collinear points. In our everyday life, we see objects which are round in shape, such as wheel of a car, a dart game, a dial of a wall clock, and a coin. Observe the seconds hand of this clock. Its tip moves in a round path. This path, traced by the tip of the seconds hand, is a circular path. The collection of all the points in a plane, which are at a fixed distance from a fixed point in the plane, is called a circle. The fixed point is called the center of the circle. O is the center. The fixed distance is called the radius of the circle. Length OP is the radius of the circle. A circle divides a plane into three parts. The first part is the area inside the circle, which is called the interior of the circle. The second part is the circle. The third part is the area outside the circle, which is called the exterior of the circle. The circle and its interior together makes circular region. If we consider 2 points, P and R, on a circle, then line segment PR is called the chord of a circle. A number of chords can be created in a circle. If the chord passes through the center of the circle, it is called the diameter of the circle, which is equal to 2 times the radius. Diameter is the longest chord. AOB is a diameter of the circle. A circle can have more than one diameter. The length of the complete circle is called its circumference. A part of the circle between 2 points on that circle is called an arc. The longer part of the circle is called the major arc PQ, and the shorter arc is called the minor arc PQ. When these 2 points are at the ends of the diameter, then the major and minor arcs become equal to each other and are known as semicircles. The region between a chord and either of its arcs is called segment of the circle, and depending on the arc, it is also divided as major and minor. Major segment for major arc and minor segment for minor arc. Similarly, the region between the center and the arc is called the sector of the circle, and again, depending upon the arc, it is divided into major and minor sectors. Equal chords of a circle subtend equal angles at the center. It is given that AB is equal to CD, and they are chords of a circle. We need to prove that angle AOB is equal to angle COD. In triangle AOB and triangle COD, AB is equal to CD. OA is equal to OD, as they are radii of the same circle. Similarly, OB is equal to OC, as they are radii of the same circle. Hence, triangle AOB is congruent to triangle COD by SSS congruence. Thus, angle AOB is equal to angle COD by CPCT. Let us see the converse of this theorem. If the angles subtended by the chords of a circle at the center are equal, then the chords are equal. It is given that angle AOB is equal to angle COD. We have to prove that the chords AB and CD are equal. Since triangle AOB and triangle COD are congruent by SAS congruence, hence AB is equal to CD by CPCT. The perpendicular from the center of a circle to a chord bisects the chord. It is given that AB is a chord and OM is perpendicular to AB. We have to prove that AM is equal to MB. In triangle AOM and triangle BOM, OA is equal to OB because they are radii of the circle. OM is common in both the triangles. Since OM is perpendicular to AB, hence angle OMA and angle OMB are both 90 degrees. Thus, by RHS congruence, triangle AOM is congruent to triangle BOM. So, AM is equal to BM by CPCT. Let us prove the converse. The line drawn through the center of a circle to bisect a chord is perpendicular to the chord. In triangle AOM and triangle BOM, AM is equal to BM since OM bisects AB. OM is the common side. OA and OB are radii of the circle. Hence, both these triangles are congruent by SSS congruence. So, angle OMA is equal to angle OMB by CPCT. Since AB is a chord and M is a point on it, angle OMA is equal to angle OMB, which is equal to 90 degrees. Equal chords of a circle are equidistant from the center. It is given that AB and CD are two equal chords. We have to prove that their perpendicular distance from the center, OM and ON, are equal in lengths. In triangle OMA and triangle ONC, OA and OC are equal radii of the circle. Since OM bisects AB and ON bisects CD, hence AM is equal to CN. Since OM and ON are perpendicular bisectors of AB and CD, hence angle OMA and angle ONC are equal to 90 degrees. Thus, by RHS congruence, triangle OMA is congruent to triangle ONC. Hence, OM is equal to ON by CPCT. Let us prove the converse. Chords equidistant from the center of a circle are equal in length. Here, OM is equal to ON. We have to prove that the chords AB and AC are equal. Since OM and ON are perpendicular bisectors, hence AM is equal to MB and AN is equal to NC. It can be proved that triangle AMO is congruent to triangle ANO by RHS congruence. Hence, AM is equal to AN by CPCT. From both these facts, we can prove that AB is equal to AC as shown. There is one and only one circle passing through three given non-collinear points. If A, B and C are three non-collinear points, and when they join each other, a triangle is formed which is termed as triangle ABC. The circle passing through these points is called the circumcircle of the triangle ABC. Its center O and radius are called respectively the circumcenter and the circumradius of the triangle.
Visit Atech Academy on www.atechedu.com or contact on 90411527777.